So far we have learned about flow. Today, let's see what kind of application we can get from the flow theory. So let's recall some concepts from the flow theory. Concepts from the, not flow theory, the undergraduate graph theory. In undergraduate graph theory, we learned some theorem called Mangle Theorem, which relates the graph connectivity and then the number of disjoint passes between two vertices. So such a theorem can be also proved using flow theory. So let's recall several concepts that we learned in the undergraduate graph theory. For two vertices x and y in graph, we say set S is an xy separating set. If in a graph, if you delete these vertices in x, S, then the remaining graph is, in the remaining graph, there is no passes from x and y. So from starting this x, there is no way that you can get to y without using the vertices in S. So in this case, we call this S as a xy separating set. And we write the kappa of xy to denote the minimum size of such a separating set which separates x from y. And we say that several passes from x to y are independent if they share no internal vertices. For example, we have these three passes. They all share the endpoints x and endpoint y, but their internal points are all disjoint. And we write lambda of xy for the maximum number of independent xy passes. So for example, in this graph, if you take this is one path, and another path, this is another path, and let's say this is another path. As they don't share any internal vertices, they are independent passes from x to y. So in this case, you can easily check that the kappa of xy is 3, and then lambda of xy is 3. So they are same. One thing you can easily see is this kappa of xy plays the role of the upper bound for this lambda of xy. Because once we have deleted the vertices in S, there are no paths from x to y. Which means in this, if we have several independent passes from x to y, each path must use at least one vertex from this set S. So we get this inequality. What Menger theorem essentially asserts is that we have an equality in here. And also this holds for edge version as well. So we add a prime to denote that these parameters are defined for the edges. We say kappa prime of xy with the minimum number of edges whose deletion makes, y unreachable from x, meaning that after deleting edges, there are no passes from x to y. And lambda prime xy with the maximum size of a set of pairwise edge disjoint xy passes. So for example, if we have, say, these two set of passes, and let's say this is x and this is y, then these two passes are not independent because they share internal vertices, this internal vertex. However, they are edge disjoint because they don't share any edges. So in this case, you can easily check that the kappa prime xy is 2 and lambda xy is also 2. No matter which one edge you delete, always the leftover is a connected graph. On the other hand, kappa of xy is just 1 and lambda of xy is just 1 because this S is a xy separating set. And then you can also, every path from x to y must use this specific vertex B. So that gives us that the lambda is 1. And this also gives the definition of the connectivity. And connectivity of G is the number of vertices minus 1 if G is complete. Otherwise, this is same as minimum of kappa of xy for all non-adjacent vertices. Non-adjacent pairs xy if G is not complete. And this is called connectivity of G. A simple version of Mangle theorem asserts that if G is K-connected, meaning that its connectivity is K, again this is kappa, not K, then for any two vertices x and y, we can find at least K independent paths. So that's one version of Mangle theorem. But let's write it in more general, more stronger form. Say if x and y are vertices in a possibly multigraph. For multigraph, the vertex connectivity is, same with the simple graph. You just, you replace all the multi-edges with single edges. Then the vertex connectivity doesn't change. But for edge connectivity, it actually matters whether the graph is multi-graph or simple graph. For example, this has edge connectivity 3 because in order to disconnect this, you need to delete all 3 edges. But this has edge connectivity 1. So if this is multigraph or graph, or even digraph, then kappa xy equals lambda xy when xy is not an edge of G, or edge version says that kappa prime xy equal lambda prime xy, say for all pairs xy of the vertices in the graph. So all the definition above also works for the directed graph. For directed graph, we define this path as a directed path. Then all this separating set independent all makes sense. So there you can also define in a same way. So we want to prove this Mangle theorem. Then we can actually prove this using flow theory. So in undergraduate graph theory, we proved it using other technique. We directly prove it by using the concept of barrier and others. But using flow, we can prove it. So how do we do it? We have a graph, and we want to convert it into a network. And network must have a source or sink. Sometimes we want to artificially add them. Sometimes we want to designate certain vertices as a source or sink. So let ST be the source and sink with S being X and T being Y. So since we are interested in the passes between X and Y, it's natural to take x as the source and t as the y as the sink. And let's consider directed H version first. So digraph, and we have the H version. We assume G is a direct graph, and we want to show that this equality holds. How do we do it? We have this graph. So this is S, and this is T. We have this digraph. Say this is a directed graph. And we want to make it as a network. For that, we designate the source and sink. And we also have to assign some capacities for the edge. So what we do is we want to assign each edge a capacity 1. So now each edge has a capacity 1. Then what happened? By applying the max flow Menger theorem, and we use the flow integrality theorem. So what was the name that we assigned to the theorem? Give me a moment. So I think flow integrality theorem, that's what we called. Yeah. And flow integrality theorem. We have the conclusion. Kappa prime xy is lambda prime xy. Because what this lambda prime xy is. So we have by maximum flow, if we have a maximum flow, and then flow integrality theorem implies that there exists an integer maximum flow, integral maximum flow. But this integer could be either 0 or 1. So you just check that all the edges which has flow value 1, you just color it. Then for each vertex, if one incoming edge is colored, then one outgoing edge must be also colored. So you assign that this and this and this. So every vertex, if say certain number of incoming edges colored, then the number of outgoing edges colored must be also same. So if two incoming edges are colored and two outgoing edges are colored, then you take from here, you can, from S, you take one edge which is colored, and then next second edge which is colored until you reach to T. And then you delete this, and the remaining one you repeat this. Then you can keep pulling off the passes. And how many passes can you pull off? Exactly the same as the maximum flow value. Because each time you pull off this path, this contributes 1 to the flow value. So this is same as maximum flow value. Because this lambda prime is maximum number of independent passes. And what's this kappa prime xy? Kappa prime xy is defined as max cut, maximum cut size. Because once you have S and T, and then you let's throw it in black way, and then you deleted some edges, and then now this is disconnected. Then you take all the vertices which are reachable from this S, and then let it be S, and rest of them is T, which is the complement of S. Then the number of deleted edge must be all the number of edges between S and S complement. Because all the edges from S to this T must have been deleted. If one of them is not deleted, then this vertex also is reachable from S. So which is a contradiction to the definition of this set S. So this is exactly same as the capacity of this source sink cut, because all the capacity of this edge is 1. So you can easily check that this is mean cut. Then Max-Flow mean cut theorem says that these two are same. So which is the conclusion that we wanted. And for directed vertex version, what we do is we have, say, this digraph. Yeah, let's consider this simple diagram. What we do is we consider a U graph. So we still have S and T, and every vertex we tear it into 2 vertices. So this V is now split into V1 and V2. And in these two, this is actually directed edge. And then for any incoming edge of V, we add it here. And for all outgoing edge of V, we add it to V2. Then you get this new directed graph. Then if we have, say, 2 vertex disjoint passes here, then that corresponds to 2 vertex disjoint passes here, and then the other way also holds. So if we have, say, 2 edge disjoint passes here, then this edge and this edge are used. So second pass cannot use those edges anymore. But this edge corresponds to the vertex here. So these passes actually corresponds to passes here, which are vertex disjoint. So lambda prime st is same as lambda st in this graph. So G, say this is G, this is G prime. And in the same way, you can actually show that once you delete some vertices here, has the same effect of deleting edge here. Because when we find the path, if we have a path passing through a certain vertex, there should be an incoming edge and outgoing edge. But if you delete this one blue edge, then there is no way that you can use, any of these incoming and outgoing edges. So deleting these edges has same effect as deleting vertex. So from that, you can easily check that the kappa prime in this G prime is same as kappa of G ST. Since we already proved the H version of Menger theorem, so you apply H versions of Menger theorem here to show these two are same. Then, because these two are same and these two are same, so we can actually conclude that these two are same. So that's directed vertex version. And also, undirected graph version can be followed from the directed version by replacing each undirected edge into two directed edge. And then you just argue a bit, then you can prove the undirected version. One thing you need to be a bit careful is that when you want to find some, edge disjoint passes, and if one path use this, say, UV in one way, and then the other path uses the other one the other way, then in the directed graph, these two paths are actually edge disjoint, but in the original undirected one, those two are not edge disjoint. But you can actually argue a bit that in that case, you can actually change it into these two graphs, two paths, this path and this path, and we forget this edge, which is essentially the same technique as we proved in the flow theory. We proved the algorithm for the max flow Minkowski theorem works. In there, we have Pi and Pi plus L. We take the union and we find the two paths Q1 and Q2. So this red one is like Q1 and this green one is like Q2, while the black one is like Pi and blue path is like Pi plus L in a philosophical level. Anyway, so you can check yourself for the undirected version. So this shows that we can prove the Mangle theorem.